First and foremost, it is organized by atomic number, okay? If you look at the periodic table, it goes in order of atomic number. Now, generally, that also means it's going in order of increasing atomic mass. There are a few exceptions to that, but it always goes in order of atomic number from left to right, then top to bottom, right? So we move across, then we move down. In a more general sense, it's organized into what are called groups and groups and periods, okay? So groups are the ones that go up and down. They are the columns. That'll be by far the way we reference the periodic table the most. So we really need to know what a group is, okay? What the groups are. Periods are how they label the horizontal rows on the periodic table. They give us less information. Okay, there's less organizational system within the periods, and so they're not as important to us. But vertically, a column on the periodic table is very well organized, and they behave really similarly. And so groups are really, really important, okay? Sometimes groups are called families. You will not really hear me reference them as families, but sometimes on CK12 or in your book, you might see them called a family. That's just not typically how I will reference them, okay? But within a column or a group, right, up and down here, elements are similarly, they have similar properties, okay? So elements within the same group on the periodic table will behave similarly, okay? Across a period, things change pretty dramatically as we move left to right on the periodic table, okay? So let's take a look take a look at potassium, where potassium is, okay? And if we move all the way over from potassium all the way through over here to krypton, they're in the same period, but they behave so differently, right? Potassium is a metal. Krypton is a non-metal. Potassium is a solid. Krypton is a gas, right? They behave very similarly, or very oppositely, okay? Oppositely, is that a word? Differently? Yeah, sure. It's a word for today. Okay, so potassium is very reactive, and krypton is not reactive at all. They have very different sets of properties. So we're not concerned a lot with periods, okay? However, we do need to know that in general, things that are clumped together on the periodic table do tend to have similar properties. So they'll behave like things in their group, but they'll also behave similarly to the elements that are kind of grouped around them, okay? So potassium and calcium probably behave pretty similarly to rubidium and strontium, right? They kind of sit in that same general area, okay? I want to do a little bit of labeling, so I want you to take out your periodic table. And I want to label some groups here so that we have an idea. When I reference a group number, I want you to be able to know where that is, okay? And so we're going to put in here this periodic table in particular is already labeled, okay? It's already labeled 1 through 8, okay? And they're labeled 1A, 2A. You don't need to put the A on there. But I would like you to have your groups labeled. Group 1, 2, we skip these middle guys. 3, 4, 5, 6, 7, and 8. Okay, so I do want you to have those labels above your periodic table groups. Okay? Some periodic tables will label them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then they pick up 13, 14, 15, 16, 17, 18. Okay, that's not my preference because having labels with these group numbers allow us to see really clear patterns about things. Okay, so we're going to identify some of those patterns here in just a minute. But yeah, Maddie. Okay, go grab it. Okay, so I would like for you to have the label 1 through 8. If you ever hear something that's labeled or you have a reference to group 17, that would be the same as our group 7 right here, right? We're taking out the 10 groups in the middle and we're relabeling them. So if you hear a reference to group 16, it would be the group that starts with oxygen, right? The same as group 6. So I like to reference them 1 through 8, but you will see other sources might reference them 1 through 18, but I'll show you why I think it's important here in a little bit. Okay, so 1 through 8 is going to be how we label them. On your periodic table, okay, we're going to talk about the three main categories of the periodic table. The 3 main categories of the periodic table. Okay? The 3 main categories are metals. What else? What's the opposite of a metal? Okay, yes, but they have non-metals. Good. And then there's the middle guy. What's it called? It's like a smush between them. Yeah, what do you think, Ethan? Metalloid. Perfect. A metalloid, okay? So we have metals, non-metals, metalloids, and we're going to fit them, this periodic table, into 3 categories, okay? So metals, here's a bunch of properties of metals. They are shiny. They're good conductors of heat and electricity, okay? What does it mean to be a conductor of heat or electricity? What's that mean? Yeah, what do you think? Yep, good. It travels through it. Travels through. Okay, so metals, once they get hot, right, they stay hot. Electricity moves through them, right? Though they are good conductors of heat and electricity. Most of them are solid at room temp. Do we know any exceptions? Bless you. Do we know any exceptions to that? There is one exception to a metal that is not a solid at room temperature. It starts with an M. It's typically in a thermometer. Yep, mercury. Mercury is our exception to that, right? It is a liquid at room temperature. Okay, so it's an interesting little guy. Most of them are what we call malleable. That might be a new term for us. Do you know what that means? That's right. Easy to move, easy to mold a little bit. And we think of it as we are able to like pound it out into kind of thin sheets. Okay, we're able to manipulate that. Okay. So I'm just going to put able to manipulate. And then I'm just going to put /sheets, right? We can make it into thin sheets. Okay, so what are some metals? You can look at your periodic table if you need to. But what are some metals that might be example of being really malleable? Just shout them out. What do we think?
Iron.
Iron, okay.
Copper.
Nickel. You're missing 2 really big ones, I think. That is a metal. I don't know much about its properties, but... Okay, yeah, gold. I would agree there. Yes, we're missing 2 really obvious ones. What are things that you have in your household that are metal sheets? Aluminum is one. What's another one? Tin, right? Tin cans and all that kind of stuff. But yes, gold, silver, right? They have little thin sheets of that. Iron is a big part of steel, right? Steel is a mixture of a bunch of different metals, but iron is a big component of that. Yeah. All right, the next one is to be ductile. And this says it can be drawn into a thin wire. So what are metals you think of that are good examples of having ductility? What do we make most wires out of? Yep, copper is a good example. Even lead, right? A lot of pipe is made out of lead, right? That is able to be drawn out like that. But those are all good examples of that. Okay. Metals have high tensile strength. Okay, that just is basically, I don't have a good definition for that, except that it is the opposite of being brittle. Okay, it's the opposite of being brittle. So that means when you hit it, it's not going to shatter, right? It's just not going to shatter like that. Some metals have lower levels of tensile strength, but most of them have a high tensile strength, okay? Some of them have different properties. I had up here mercury is a liquid. Some of them are very, very soft and can be cut with a butter knife. So we're going to look at some metals that are like that. And I don't know why my last point got cut off here. What's that last one say?
Some are very hard, like.
Oh, okay. Okay, perfect. Any other points on there that got cut off my slide? We're good? Okay. All right. So here's some examples and pictures of some metals. The first one up top there is an example of a group 1 metal. It's very, very soft. It almost has the texture of like cold butter, right? You can cut it with a knife, but it is still a metal, okay? This one over here almost looks fake, right? How shiny it is, but some of them have a really high shine. The bottom left is an example of what characteristic? Being ductile, right? Because it's a wire, and it's an example of conducting heat and electricity, right? We see that. And then over here on the edge, what do we look like? What do we think that looks like? I mean, does it look like it has high tensile strength, or does that look like a kind of a brittle metal? If you had to guess, what do you think? I think that looks pretty brittle. So that might be a metal that sits farther on this side of the periodic table. Okay, we'll kind of look at that as we go. But those are just some examples there. Okay, so that's our first category of elements, okay? Now the opposite side of the periodic table are called non-metals. What are some examples? Can you just pick out a few non-metals off your periodic table? Hydrogen, what else? Oxygen, carbon, right? Nitrogen, all of those guys that sit in the top right are non-metals. Okay, so they essentially have opposite characteristics of metals. They are gases at room temp. If they are a solid at room temp, they're very brittle. And then they are poor conductors of heat and electricity. Why is it a good thing for us that they are poor conductors of heat and electricity? Because what'd you say? That's right. It's all around us. So if the oxygen around us was conducting heat and electricity, that would be a problem for us, right? That would be flowing through us constantly. It would not be good, right? So they are not good conductors of heat and electricity, which is good news for us, okay? All right, last category is like the smush in the middle here called metalloids. This is only a small number of elements on the periodic table. There are not very many metalloids. And what happens with a metalloid is that essentially they have characteristics of both. Okay, they have a little bit of the best of both worlds. Most are solid at room temp. They are less malleable than true metals, but they are not as brittle as non-metals. So they just kind of fit right in between. Some of them are really shiny. I'm going to show you, I have the picture down there of antimony. See, it's nice and shiny. Antimony on your periodic table is SB. You see where it sits right here? Okay. So the metalloids kind of sit in the middle there. And then I'm not sure why my picture's covered up my other words there, but it's got a little other information about metalloids, okay? What's the next point say? Sorry, I don't know. Oh, you don't have it. It's covered up on it. Okay, fine. This must not have been that important then. Okay. All right, so I would like for you now, we're going to take just a few minutes to kind of shade our periodic table or outline our periodic table in these three categories. Metals are red, non-metals are blue, and the metalloids are yellow. So I'm going to give you a couple minutes. All right, while hydrogen seems out of place being in group 1, we're going to talk about why it does sit there in just a second. Remember I mentioned there's some patterns that we're going to see on the periodic table. Hydrogen fits really clearly into one of those patterns. However, it doesn't fit along with the metals in the rest of that group. So hydrogen is still a non-metal, right? But it sits in group 1 because of its electron structure. And so we're going to talk about that here in just a minute. But it is still a non-metal sitting in that spot. Sometimes you'll even see hydrogen drawn in right here. Right? Like it sits over on that side too. But that's pretty rare, right? The standard periodic table is that you have it over on the left in group 1. Okay? So now we're going to spend a little time going through some of the main groups on the periodic table. So you can go back to your notes page. If you're not quite done with your periodic table, just hang on to that. You can kind of finish it as we get some time at the end of class. But we're going to go through some of the main groups on the periodic table, kind of individually to look at some characteristics and see some more of the patterns that we see develop. Okay? So we've got the three main categories of our periodic table, and now we're going to assign some groups a little bit more detail. Okay? We're going to start with group 1. Group 1. So where does group 1 sit on our periodic table? The very far left. Okay, so group 1 includes hydrogen, but if we're talking about the alkali metals, we leave hydrogen out of that, okay, because hydrogen is not a metal. So the alkali metals include all of the other elements in group 1, lithium all the way to francium. Okay, all of the group 1 metals have kind of a silvery appearance and they're very soft. So that picture that we saw of the metal, that kind of we said had the texture of butter, was a group 1 metal. All right, and so they're all soft like that, and they all have that silvery appearance. Sorry, I have a video here I want to watch, but I know it's not going to work off that link, so I'm trying to get that pulled up. Okay, these guys, this is really important. They are not found in nature as free elements. That means you won't walk around and find a chunk of sodium metal. Yeah, it's not going to happen, right? It's because they are so reactive, especially with water, that they are not, they wouldn't survive, right, in nature, right? I say survive, but you know what I mean. Like, they wouldn't last. They would be too reactive. They would react with things all the time. And so they are not found in nature. They want to bond with something. They do better when they are bonded with something else and they are a part of a compound, right? That's what group 1 is better. All right, here is the part where I want us to start picking up some patterns. It says group 1 elements have 1 valence electron. You will see me abbreviate valence electron like that. Okay, valence electron. Does that term sound familiar? A valence electron? And a valence electron is electrons in the outer shell. Okay, they are outer shell electrons, which means they are the only electrons for that element that are available for bonding. They're the only electrons that are available for bonding. So I want to do a deep dive real quick into like an overview of electron shells. And I'm going to draw a little image here that's not incredibly accurate, but it gives us a visual, at least, of electron shells, okay? So let's say that I'm looking at sodium, for example. Okay, here is a basic overview of sodium's electrons. The first shell of any atom only has 2 electrons in it. The next shell has 8. Okay, have you heard that before? We need 8 electrons to have a complete shell. Sodium has a total of how many electrons? So take a look at sodium, Na. How many electrons does sodium have? Neutral sodium. It has 11. So far I've got 2 plus 8, which is 10. So I've got 11 electrons. That just kind of gives us a visual of sodium's electrons. It's not super accurate, but it gives us an idea. Okay, so sodium, it wants to have a full outer shell of electrons. So its choice is either to gather in 7 electrons from something else and someone else, or its choice is to give away its 1 outer electron, and then we can remove that shell to be left with a full shell. So what do you think sodium chooses to do? Gather in 7 or take away 1? Give away 1, right? Or take away 1. So sodium all the time, will want to give that electron away. That's what makes it so reactive, right? When we say it's reactive, that means it wants to bond with other things readily, right? Because it only has 1 electron it needs to get rid of before it's happy, right? Before it is complete. It wants that outer shell to be full. So rather than try to gather 7, it wants to give away 1 electron. Okay? But here's the pattern I want you to see. Elements in group 1 have 1 valence electron. Okay? That's the pattern. Elements in group 2 will have 2 valence electrons. Okay? That's a main thing that we need to see. All right, I want to show us here a little video of these group 1 shells. Okay. Sorry. Here we go. Okay. Jack, do you want to grab the lights for me, please?
Lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkaline metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now,
Okay, so did you see what he said? Did you hear what he said? The reaction will occur with water, and that reaction gives off, right? A product of that reaction is hydrogen gas. And so that's what you're going to see happening here in just a minute with these other metals, is that the reaction gives off heat when that happens, and it will catch that hydrogen gas on fire. And so that's where you're going to see this reaction becoming more aggressive as they go down. But as they work their way down the periodic table, the reaction gives off more heat more quickly, and it will catch that hydrogen gas on fire.
Same sort of thing happens, although the reaction is a bit more vigorous. All the alkaline metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a light flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkaline metal.
Whoa, that's cool.
Pretty crazy, right? So even if you were to handle, Jack, can you grab the lights for me? Even if you were to handle lithium, sodium with your hands, it would be enough moisture from your skin and your hands, you would get burned, right? So it's just enough. It doesn't take a lot, but you can't handle, right? Those things aren't found in nature anyway, but you could not handle those elements with your hands, because even the moisture in our skin would be enough to cause a burn, right? Not a light on fire burn, but enough to cause an irritation or a burn.
So does that have to do like Alka-Seltzer? Like how much is a little water?
Yeah, that's a little bit of a different reaction, but it's the same principle, right?
If it's not found in nature, how do we get it? Like,
Well, we discovered it in nature, right, as a metal, but it exists in our world more commonly in a compound.
Okay.
Yeah. So it's not something that, I mean, I can't say you'd never find it in nature, right? Because it had to be discovered somewhere somehow. But in general, it exists for us in a compound form. Yeah, good question. All right, let's move to group 2. Let's see if I can get this back up here. Group 2 is called the alkaline earth metals. The alkaline earth metals. Okay, and they are in group 2. All right. They have a little bit more of traditional metallic properties than group 1, so they're a little bit more dense. They're a little bit higher tensile strength, a little bit harder. They typically have higher melting points, and they are a little bit less reactive. However, they are still too reactive to be found in nature. So here's an example of calcium metal, but we don't see calcium metal floating around in our milk, right? We don't see that. But we know that milk contains calcium. But it contains calcium in the form of what? Yes, a liquid, but it contains calcium as a compound. And then our body extracts what it needs, right? It will break down those compounds and extract what it needs. So it's not like pure calcium metal in our milk, right? It's in the form of a compound. Group 2, we said, has 2 valence electrons. That's a really important pattern. So let's think about the group 2 elements. How many valence electrons would they need to gather to be complete? They would need to gather 6, or they could give away 2. So which would they rather do? Give away 2. Okay, so they are still really reactive because they can find 2 elements to give those 2 quickly. Okay? All right, we're going to skip, or we're going to walk through here these groups 3 through 12, or we don't always label them 3 to 12. I'm not going to do that, but these are called the transition metals, and they're the big chunk right in the middle. On our periodic table, it's the big red group right in the middle, but they're called the transition metals, and they contain most of the metals that we consider to be like typical metals, right? Silver, gold, copper, iron, zinc, all the things that we typically think of as metals are found here, with the exception of like lead. But when we typically think of metals, those are found right there in the transition elements. They have typical metallic properties, so all the things we talked about earlier. However, they don't follow a particular pattern when it comes to valence electrons. So it's a less predictable set of elements for us. They don't follow any discernible pattern when we're talking about valence electrons. Okay, that's why we skip them over when we number them, right? Because we pick back up with group 3. All right, we're not going to talk any about boron, carbon, or nitrogen's groups. They don't have a whole lot going on. But if you had to guess for nitrogen's group, right, how many valence electrons would you guess nitrogen's group is going to have? 5, because they're group 5, right? So there's not a lot else we need to say about that, but we're going to move over to group 6, which is called the chalcogens. That's oxygen's group. So I have it labeled here group 16, but I want to change that to a 6, okay? That way we're consistent. So let's change that to 6. These guys are pretty reactive. They have 6 valence electrons. I think that's the point that's cut off on the bottom there on my slide. I don't know if it's cut off on yours, but is it cut off on yours as well? No. Okay, it's just mine. These guys have a wide range of properties, because if you look at your group 6, you'll see you've got nonmetals and a metalloid in there and a regular metal. So we change a little bit as we go down that group. If you go even further down, you'll see some man-made metals, which our periodic table doesn't have those all built in yet. But in our element system right now, there are 35 man-made elements. 35 man-made elements. I would maybe highlight that, right? Circle that. That's a fun number to know, okay? There are 35 man-made elements. If you had to take a guess and look at the periodic table, what are some elements do you think that might be man-made? Take a look. Some of them have really interesting names. Rutherfordium, Californium, Einsteinium, right? Yep, all of these ones down typically in the bottom and in the very bottom. Those are, some of those, we call them super heavy elements, are man-made. And nobelium, lawrencium, mendelevium, right? People got to name them however they wanted. And so a lot of them are named after famous scientists. There's americium, right? So berkelium, things like that. Those I would guess, so those would be man-made. Okay, I can't necessarily say that for sure, but I would guess. Yeah. Okay, group 7 is called the halogens. Okay, the halogens. They are very, very reactive non-metals. Okay, let's try to brainstorm here about why would they be so reactive. Yeah.
Because they're trying to get valence electrons.
Okay, good. And how many valence electrons do they need?
Just one.
Only one, right? They only need one electron. So they will take that electron from anything, most likely a group 1 metal, right? Those two pair together really well, and they make something, a category of compounds called salts, right? But they are really, really, really reactive. They can be gas, liquid, or solid at room temperature. They're usually so reactive, they're not found in nature as well. Typically, they are gases, okay? So if they're found in nature, they are found as a gas. But even the compounds that we think are familiar to us, like what do we see fluorine or fluoride used in? At the dentist, right? With teeth, right? It helps with enamel and teeth. But it's not pure fluoride or pure fluorine, right? It's a combination, a compound of some sort. Same with chlorine. Where do we see that used in? pools, right? And so it's not solid Cl2 or Cl, right? It's a compound of some other additive in there. Iodine, you know what iodine's used for? What's it used for? It is used in medicine. It is an anti-infectant or antibacterial, right? It's like a surgical scrub, right? Before you have surgery, they'll scrub iodine on you. What color is it? No, it's like brown, orangish, right? It leaves kind of an orange stain on your skin, right? But that's used as an anti-infectant. That's probably the closest we get. I mean, I'm sure it's a compound, but it's pretty true iodine. I'm sure there are other things added into that, but that's probably as close as we get. Okay, so that's the group 7 elements, and then lastly, we'll call them group 8, are the noble gases. The noble gases, okay? These guys are generally really unreactive, and so why do you think that might be true? Why do you think that this group of elements is unreactive? Yeah.
Because they have all of their shells.
They have all 8 electrons already. They don't need anyone, right? They're independent. They don't need anything, okay? All of them are gases at room temperature, hence the name, and they have full outer shells. This is like just a fun little thing about the noble gases is that we typically consider neon lights, right? Here's neon right here, as just neon lights. But in all reality, we use a mixture of these gases to come up with different colors of neon lights, right? So neon lights are actually made through the emission of multiple noble gases and a mixture of those things, right? I don't even know what color pure neon puts out, but a mixture of those gases get us all the different colors of true neon lights. But the one in our classroom starts with lanthanum and actinium, okay, or actinium, I guess. Down here below, that's why they're called the lanthanides and actinides. On our periodic table, it actually sticks lanthanum and actinium right up in the periodic table. Either way is fine because this is where they sit, right? It goes from 56 to 57, right? They would slide up and fit right in here, okay? And so that's really where they sit. So where they get bumped down kind of depends on the periodic table and the printing of that. It doesn't really change much in how we look at it. But those are the lanthanides and the actinides. The lanthanides is the top row of them. They behave similarly to group 2 metals. And then the actinides are all radioactive. They're the bottom line right there. They're radioactive. Several of them are man-made, but they're the little bit more dangerous of that group, right? Radium would sit next to actinium, right? You know, radium is really dangerous. That was the Madame Curie problem, right? Was with radium, that radioactive, that she didn't know it was radioactive, right? And so then they all got sick, but that was the discovery of that. Okay? If we were to sit the lanthanides and the actinides in the periodic table, this is what it would look like. So it becomes a little less aesthetically pleasing, right? A little less organized. And so really the only reason the lanthanides and actinides get pulled down is for like space saving purposes. There's no other reason that they get pulled out, but that's really it. Okay. I don't think I need to do anything with that, so. Questions about charge. Okay, they all have a +1 charge. Tell me, how many valence electrons did we say that group 1 elements had? 1. Okay, so let's go through this one more time. If I was looking at sodium, sodium has 2 in its first shell, 8 in the next one, and then 1 in the outer shell, right? That's what we gave you. We said sodium wants to give away its outer electron. We agree with that? Okay, if it starts with 11 electrons and we give 1 away, how many are we left with? 10 electrons. And what charge does that leave sodium with? No, it's supposed to have 11, but now it only has 10. It leaves me with a +1 charge, right? I'm supposed to have 11, but I'm short 1. I only have 10. So that leaves me with a +1 charge. And so that's where all of these elements get their charge from. They want to give away an electron. Okay, so potassium normally has 19. It wants to give away its outer electron, leaving it with 18. So it's supposed to have 19, but it only has 18, which means I have one more proton than electron, which means I've got a positive charge.
So does it want to just be like, is it, I'm confused. So is it usually just neutral?
Yeah, everything on the periodic table by itself is neutral. But when we start dealing with how things bond, they will take on that charge because they want to give those electrons away.
Then they become positive.
And then they'll bond with something else who will take that electron from them.
And then if you take it away,
If I take an electron, from someone, if I was neutral and I took an electron on, then I would have a negative charge, right? Because I would have an extra one. Yep. So now let's look to the other side of our periodic table at group 7. They have 7 valence electrons. They want to do what? They want to do just that. They want to take in an electron from somewhere else to have 8, right? So if I'm going to add an extra electron to myself, what charge does that give me? -1. So look at all of the elements in group 7. Fluorine, chlorine, bromine. What's all their charge? Negative. And there's no 1 written there, but we assume 1. Okay, -1. Do we see how the charge has a correlation to its valence electrons? A little bit, right? I just want you to see that these charges aren't arbitrary. They're not just randomly assigned, right? They have a purpose, and there's a reason they have that particular charge, okay? Let's look at nitrogen's group, for example. Nitrogen has 5 valence electrons. So what's going to be easier, for them to give away 5 or to bring in 3? To bring in 3. So if they need to bring in 3 extra electrons, that would leave them with a charge of -3. Is that what all nitrogen's group has a charge of?
yes.
Until we switch down and start talking about metals. Yes, right? All the anions there have a negative charge. Okay, so do we see how that works? All right, I want to show you here just a quick pattern with all these. Okay, it's not erasing, I don't know why. There we go. Okay, our charges work outside in. -1, I'm sorry, +1, -1. +2, -2. +3, -3. And this group right here is plus or minus 4 because with 4 electrons, I could give them or take them just as easily. Okay, so do you see how those charges work inside out? We skip these guys, right? But our charges kind of make a pattern. Okay, so our periodic table actually shows us a lot of information there. Okay? All right, let's actually get... All right. Okay, what is an ion? We talked about this yesterday or 2 days ago, whatever, last class. What's an ion? An ion is any atom that has a charge. An ion is any atom that has a charge. And what's a positively charged one called? Okay, that not a proton. I'm talking about what is a positively charged ion called? A positively charged one. A cation, right? Remember, it's called a cation, right? Cations are positively charged, anions are negatively charged. So we're going to start looking at how we name compounds here in just a second. But these are the 3 categories of compounds we're going to learn how to name, okay? The first of which is called an ionic compound. It's called that because it has to deal with how these atoms bond, okay? But it is between a metal and a non-metal. So I want you to look at your periodic table of ions, okay? Take a look at this. The metals side of my periodic table is the whole what? Left or right? Metals are on the left side of my periodic table, and nonmetals are on my right, right? If I had to split them from the stair step, metals are to the left, nonmetals are to the right. Every metal has what type of charge? A positive charge, okay? So the metals are cations, and the nonmetals are anions. That's really important, okay? So an ionic compound is between a metal and a nonmetal, or you could say it's between a cation and an anion, right? It's when we bring a positive and a negative together. A covalent compound is between 2 non-metals, okay? So this would be an example of like CO2, right? A carbon and oxide or oxygen compound would be considered a covalent compound. Okay, then the last category we're going to look at is acids, naming acids. Okay, it kind of fits into its own little rule system there, but we're going to name acids later. Okay, now, periodic table. And I want us to see some relationships here between what we just learned about valence electrons and all the charges that are here. Okay, I want you to look at all the elements in group 1. What's their charge? Positive 1. All the elements in group 1 have a positive now, so I'm sorry, I know you've been hanging in there a long time, okay? We're going to start with basic ionic compounds, which means we are going to pair a metal and a nonmetal. So something from the left side of the periodic table with something from the right side of the periodic table, okay? When we do this, our compound has to be balanced. Our overall compound has to be balanced. So that means the charge of these two things combined must equal 0. Okay, the charge of these two things combined must equal 0. Okay, here's our rules for naming binary ionic compounds. The cation always gets named first. We're always going to build compounds from left to right on the periodic table. So the cation comes first, then the anion. Okay, cation goes first, then the anion. Cation is always named first and the anion second. A monatomic cation takes the name from the parent element. Okay, that's a lot of words, but all it's saying is that a monatomic, how many atoms would that be? 1. So a single atom. So if I had calcium plus 2, it just gets to keep its regular name. That's all we're saying there. An ion, a cation, I'm trying to say all these words at one time. A cation that's by itself just keeps its regular name. And that's what our periodic table shows us, right? It still shows us that. An anion by itself ends in IDE. So look at all the anions over here. It's not nitrogen anymore, it's nitride. And that's because it's got a negative charge. Okay, so anions end in IDE. Okay? All right, we're going to just jump into some basic practice here, okay? Let's say that I wanted to build a compound between magnesium and fluoride, okay? I wanted to build a compound between magnesium and fluoride. The first thing that I do is I'm going to write each of them out with their charge. Magnesium has a charge of +2. Make sure we're on the ions side so we can see their charges, okay? And fluoride has a charge of -1, okay? If I have to make these things balanced, are they balanced right away? Can I smush them together and they're balanced right away? No, why not? A positive 2 and a -1 don't equal 0. Right? So how can I make them balanced? Yeah, Maddie, what do you think?
-1 for magnesium.
Okay, I can't change magnesium's charge. That's a good thought. Okay, what else could I do?
Could you add another fluoride?
I could add another fluorine, right? If these two are going to fit together, the ratio must be 1 magnesium to 2 fluoride atoms. So I'm going to combine them, and that means it would equal MgF2. Okay, MgF2. And then the formal written name of that compound would just be magnesium fluoride. Okay, the cation keeps its regular ending, and the anion ends in IDE. Okay, the cation always goes first. Okay, we're always going to build compounds from left to right on the periodic table. So we're always going to work left to right. Okay, let's try another one. What if I had a compound between calcium, what's happening? Calcium and oxygen. Calcium and oxygen. Okay, I'm going to write them out with their charges. Ca is +2 and O is -2. Do they fit together to be balanced right away?
Yes.
Yes, right? So all that's going to become is CaO. That's it. Okay, and the formal written name would be what? Calcium oxide. Good. It's going to end in IDE, right? And if we're not sure about that, just look at it, right? We put together O, which is -2, which says oxide. Okay? All right, we're going to turn it up one notch here, okay? I want you to give me a formula for the compound aluminum sulfide. Aluminum sulfide. Okay, I gave you the formal name. Now I want you to give me the chemical formula.
Are you not able to add like a
I can't change the charge, but I'm going to put them together in whatever ratio makes them balance. Okay. I'm going to write them out with their charges first. And I've got to figure out how can I put them together to make it work. Anybody have a guess? Yeah, Maddie, what do you think? Al2S3. Anyone else have that same thing? Perfect. That's what I had as well. How did you get there? Perfect. Okay, least common multiple between 3 and 2 is negative or 6, right? So we needed a +6 and a -6, which means I knew I needed to have another aluminum, and I knew I needed to have 2 more sulfides. That's perfect, okay? Now you want me to show you how to do it without thinking? Okay, here's what we do. All right, we're going to try this. This works for every ionic compound. We're going to ignore the plus and the minus. We're going to do what's called the crisscross method. And we're going to crisscross these down. And they now come from charges to subscripts. And it becomes Al2S3.
Does that work for anything?
It works for every ionic compound. Okay? So I did all of the same math, right? You understand the premise behind what happened, but now I can do it quicker, right? And if I needed to go through and check my charges, I could say, oh, I've got 2 aluminums. I know they're each -3. That gives me, each +3. That gives me a +6. I know sulfide is -2, and there's 3 of them, which gives me a -6, so I know it's balanced anyway, right? I can check myself, but I know that I can do the crisscross method every time. Okay, let me show you one exception to this. If I had done the crisscross method with calcium oxide, okay, if I take the 2 and the 2 down, I would have done Ca2O2. I need to reduce those down. They have to be reduced. It's got to be the least ratio between them. Does that kind of make sense? We saw, just looking at the charges, that they fit together one by one. Right? And so if we do the crisscross method, we would need to reduce those down to make it CaO, right? Ca1O1. But if it's a 1, we know we leave that off. So that's the only caveat with the crisscross method, is that you would need to reduce them at the end if necessary. Okay? All right, how are we feeling? Pretty good?
Can we do one more with the crisscross?
Sure. Yep, let's try one more. Let's try... I'm trying to find a fun one here. Iridium selenide. Okay, iridium is number 77. It's way down there in the transition metals. And then selenite is in group 6. Yeah, thank you. Okay, so you can choose either to see the ratio, or you can do crisscross, right? And so the crisscross ignores the plus minus, brings it down. IR2S4. Can I leave it like that? No, I'm going to reduce it to equal IRS2. Okay, is that comfortable? All right, iridium selenide would be our formal written name there. Okay, very good. Sorry, I know that was a lot today. Yeah, Abby, go ahead. Yep. You've got a CK12 on naming binary ionic compounds. That's posted. You have about 10 minutes, okay, left, but it'll be due before class on Friday. Okay? Sorry, I know that was a lot today. That periodic table takes just a little bit of time. We're going to do a lot more with naming in the next few days. So we'll be ready to go with that.